Hello everyone, good morning, good afternoon and good evening. My name is Vishwadeep and I welcome you all on PW Gate Wallah channel. So today we are going to start a very interesting, very easy yet very important topic, which is process scheduling algorithms. There are multiple types of process scheduling algorithms, but there are few which are very popular and very common in terms of gate exam questions like FCFS, SJF, SRTF, round robin, priority algorithms. In those 4-5 algorithms, most of the time questions are asked, and almost every year there is a question from this particular chapter. The question is almost always easy. This year also it was a very easy question, lengthy, but it was easy. So if you know how to solve such questions, then it will be very easy, just because starting point of different algorithms will be little different. Rather than that, at the end, most of the time the 80% work of all the algorithms will follow the same method. So you guys will not have a lot of different concepts to remember or understand, yet it will be very easy for you guys to score 2 marks from here. So till the last class we have discussed process states, their transitions and many other things. Okay, now we are going to start process scheduling algorithm. First, if you guys are here, please confirm if audio video both are clear to you guys and you are able to listen to me properly. Okay, CPU scheduling. To CPU, which process will run next? That is what CPU scheduling. So there are CPU scheduling algorithms. Among them, operating system will implement one, whichever is based on requirement of OS implementation. And what that particular algorithm will do, that algorithm will select what it will select. The algorithm will select one of the ready processes, that which process will run next. So what is the work of this CPU scheduling algorithm? Make a selection of what? Of one of the ready state processes to run next. Which particular ready process will run next? That selection is done by the CPU scheduling algorithm. Now, CPU scheduling algorithms are of two types. It is exactly those two types which we have seen for multi-programming. Remember two types? Multi-programming, two types, non-preemptive and preemptive. Yes, same here also we have two types of algorithms, non-preemptive algorithms and preemptive. And what is the meaning? Meaning is simple, that if a particular process is scheduled to run on CPU, then that particular process cannot be forcefully preempted, cannot be forcefully taken out of the CPU, non-preempted. If it can be forcefully taken out of the CPU, called as preemptive algorithm. Now, which algorithm is preemptive, which one is not, we will discuss one by one, and we will understand why this algorithm is preemptive and why not. Okay, before we go ahead with the algorithms, we have some times associated with the algorithms and processes. What are those times? AT, BT, CT, TAT and WT. Arrival time, burst time or service time, completion time, turnaround time and waiting time. These are the 5 times we will have to associate for each and every process. What these are? Arrival time means what? On the clock at exactly what time a process arrives in the system. Arrives means where, if you remember, a particular process first arrives in ready state. This, at what time exactly it is entering from new to ready state, that is its arrival time. So arrival time is nothing but time at which process arrives. That will be its arrival time. Each and every process will have certain arrival time. Some process, let's say, comes at 10 o'clock. Some other process is coming at 10:01, 10 o'clock and 1 minute. Another process will come at 10:30 p.m. So something like this. Each process will have its own arrival time. Second thing is burst time. Burst time or service time is the time for which a process will execute on CPU. How much time process will need CPU for execution? That is its burst time. So burst time is amount of time a process runs or executes on CPU. That is total its burst time. Now look at this. Burst time is not the wall clock time, 10:30, 10:31, 10:50. No, it is the amount of time. If I say I arrived at 6:03 in the classroom, that is my arrival time. This is the wall clock time, But amount of time is how much time I am spending in the class. Let's say I am spending 1 hour in the class. So 1 hour duration, it is a duration of time. This is wall clock time. This is 1 hour, 2 hour, 15 minutes is my duration of time. So this burst time is actually duration of time. How much amount of time for which a process runs in the CPU, that is its burst time. Are you guys having a difference and understanding the difference between time, wall clock time and amount of time? Understanding, na? Second, next is completion time. Completion time, like arrival time, it's a wall clock time. At exactly what time process completes. Let's say process arrives at 10:30 and completes at 10:35. So 10:30 is arrival time, 10:35 is completion time. What is the completion time? Time at which process completes the execution. When process completes the execution, we will have to mark that time as the completion time. Next is turnaround time. Again, turnaround time is the amount of time. How much time a particular process is spending starting from arrival to completion is the turnaround time. This is also amount of time. Okay, so it is amount of time a process spends from arrival to completion. Let's say a process arrives at 10:30, completes at 10:35. So that 10:30 to 10:35, 5 minutes system. In the system, 5 minutes the process is spent. That is called as turnaround time. Process is spent total 5 minutes in the system. 5 minutes is its turnaround time. How did I calculate? 10:35 minus 10:30, 5 minutes. Exactly what I am going to write as a formula. Turnaround time is nothing but process completion time minus process arrival time. Simplest possible formula to understand. सर आप गेट डीए प्रिपरेशन भी कराते हैं, नहीं कराते हैं क्या? बेटा गेट डीए की भी प्रिपरेशन कराएंगे, बट उसके लिए जो कोर्सेस होंगे वो अलग होते हैं. दोस कोर्सेस आर डिफरेंट, सो दोस कोर्सेस विल बी कंडक्टेड later on. Okay, next thing, waiting time. What is waiting time? See, when a process arrives, let's say 10:30 process arrived, but at whatever time process arrives, is it necessary that at the same time process will get the CPU and process will run on CPU? No. When process arrives, if some other process is running on CPU, then this process will have to wait. Wait where? In the ready state, so that when other process will leave the CPU, then my chance will come, I will run on CPU. So when a process is waiting in the ready state, how much time it is waiting in the ready state? That is the waiting time. That is the waiting time. So I am writing here the formula, but before that, the definition. Waiting time is again amount of time a process waits for CPU in ready state. That is its waiting time. But sir, how do you calculate it? Look at this. Let's say process arrives at 10:30 and completes at 10:35. This is running state and this is terminated state. Now, total turnaround time is 5 minutes. Turnaround time. We have already calculated this minus this is 5 minutes. Total time a particular process is spent in system 5 minutes after arrival till completion. But among those 5 minutes, let's assume process is spent exactly 3 minutes for running in CPU, which is the burst time of the process. So if CPU burst time of the process is 3 minutes among 5 minutes, if burst time is 3 minutes, then what is the waiting time? Remaining 2 minutes, process was waiting in the ready state. And that is what the formula of waiting time. What is the formula? Simplest formula is turnaround time minus burst time of the process. This is what we are having as the waiting time. Okay. These are the scheduling algorithms. First come, first serve. Shortest job first. Shortest remaining time first. Longest job first. Longest remaining time first. High response ratio or highest response ratio next. Priority based algorithm, round robin, multi-level queue scheduling, multi-level feedback queue scheduling. One by one, these algorithms we will discuss. Among them, the important ones are this, 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 and this. These are important ones which are only asked actually in the gate questions. Let's go with the first algorithm, FCFS, first come, first serve. See, this particular thing you have seen in your entire life everywhere. You get into the queue, whichever person comes first will get the ticket first or will get the food first from the queue. Whatever, for whatever you are waiting, if you are in the queue, follow the queue. Your chance will come as per your arrival. If you arrive early, then your chance comes early. If you arrive late, your chance will come late. Simple. As per the arrival, when you come, based on that, your service will be happening. In whichever order people are coming, in that order service will happen. In whichever order processes are arriving, in that order the processes will be executed. So scheduling criteria is what? Scheduling criteria here is arrival time. The process with the smallest arrival time will be executing first. Smallest arrival time process first. The process which is having smallest arrival time, smallest means see 10:30 a process comes, another process comes 10:32, another process comes 10:33. Which one is the smallest? This one in time. The earlier time is the smallest time. Further, what is the tiebreaker if two or more processes are coming together? If two or more processes are coming together, then the tiebreaker will be smallest process ID first. Every process has a unique ID, and whichever process is having smaller ID, that will be scheduled first. Further, type of algorithm. What is the type of this algorithm? Non-preemptive. Once a particular process goes for execution, the process will not leave the CPU unless process wants to. Okay, fine. Further, look at this. In this particular chart of process state transition, we know when a process arrives, comes first in ready queue. From here, scheduling algorithm selects one of the ready processes to run on CPU. It may have a preemption if preemptive algorithm is needed and preemption is needed. Otherwise, schedule next process and run. Processes will keep going between these two states. But just to understand the CPU scheduling algorithms properly, we are considering that processes are not having any IO requirement. So if no any IO requirement, which means process will not go into the blocked state. It will not go into the blocked state. So currently this is what we are going to follow. Ready state processes are there, whichever are arrival. Among those, scheduling algorithm will select one to run. When running process completes, it goes for terminated. If preempted, it goes for ready. Next process is scheduled to running state, and this is what we are going to follow. IO for understanding the algorithms, we will not follow that. Once we will understand the algorithms, then we will include the questions of IO also. Okay? Chal. Further, let's start the first algorithm. FCFS, I explained you smallest arrival time first, but if two processes are having equal arrival time, then smallest process ID first. Every process will have a unique ID. There is no any tie over there. Okay. Further, let's try to understand what type of questions will come and how to solve them. This chapter is purely practice based chapter. So the concepts also, when I will explain through examples only, through questions only, I will explain. Look at this. FCFS, first come first serve. Three processes are given, P1, P2, P3. These are their IDs. Look at this. Three processes all having unique ID. Their arrival time 000 given and their CPU burst time 2844 given. Now what we need to do is we need to make a chart. What is that chart? Chart is all about which process will run from when to when. That is the chart called as Gantt chart. That particular Gantt chart starts from 0 always. Remember that. Starts from 0. So at time 0, in the Gantt chart, what we will try to do? We will try to understand as per our algorithm which process will run first. Which process will run first? At time 0, I'll have to check what all processes have arrived. What all processes arrived? All three processes having arrival time 0, which means all three have arrived. If all three have arrived at time 0, all are available for selection. Now, among these three, which process will run next? Depending on the FCFS criteria, whichever is having minimum arrival time. Sir, all the arrival times are equal, sir. Then, if arrival times are equal, then we will have to go for process ID. Process ID, which one? As per the tiebreaker, smallest ID P1 will be scheduled. Now, if P1 is scheduled, what happens? P1 will complete the execution. Why, sir? Why P1 will execute? P1 will execute just because it is a non-preemptive algorithm. Process P1 cannot be preempted, cannot be stopped in between. It will complete. So if P1 will be completed, then completed for how much time? 28. So after 0 plus 28, till 28 time, P1 will run and complete. Now, two more processes are left. Among these, which process I'll have to run? Criteria, FCFS, whichever arrives first. Both are arriving at 0. Hence, I will have to go for ID just because arrival time smaller, not there. Tiebreaker, I'll have to use process ID smaller one. P2 we will run. P2 will run for how much time? 4. After 28 plus 4 till 32, P2 will run. Then At the end, only one process remaining, P3. It will be completely executed till 32 plus 4, 36. Is this clear to everybody? Is this clear to everybody? If yes, then this is what unique for each and every algorithm. For every algorithm, we need to just make the Gantt chart. After this, entire procedure is same for all the algorithms. All means all. Okay, what is the process? First of all, finding the completion time of each and every process. P1 is completing exactly at 28, P2 completing at 32, P3 completing at 36. So as per the Gantt chart, 30, 28, 32 and 36 are the completion time of respectively P1, P2 and P3. From this Gantt chart only I have written. I did not write these names randomly by myself. P1 completes here, P2 here, P3 here. Fine. After completion time, turnaround time, which is completion time minus arrival time. For each process, completion time minus arrival time. Completion time minus arrival time. Completion time minus arrival time. What is the waiting time? Turnaround time minus burst time. 28 minus 28, 0 waiting. 32 minus 4, 28 waiting. 36 minus 4, 32 waiting. Okay, what type of questions they may ask? First type of question they may ask, in which order processes are completing? Which order processes are completing? First P1 is completing, then P2, then P3. Order is P1, P2, P3. First type of question. As per the Gantt chart, we can easily understand. Second type of question. They can ask completion time of any specific process. One of these two. What is the completion time of P3? Or what is the completion time of P1? We can get the answer from here. Or they can ask turnaround time of a specific process. From these three values, you can easily tell what is the turnaround time of any specific process. Similarly here, what is the waiting time of a specific process? Like waiting time of P2 is what? They can ask, we can answer. Last, they can ask average waiting time of all the processes or average turnaround time also of all the processes. Average turnaround time of all the processes. Three processes are there. Their turnaround times are these. Average will be what? 28 plus 32 plus 36 divided by 3. This is 60 plus 36. 96 divided by 3. 96 divided by 3 is how much? 32. And average waiting time will be what? First waiting time is 0, second waiting time is 28, third waiting time is 32, divided by total 3 processes, 20. So this is how they can ask a variety of questions. Okay, let us solve one more question FCFS. Here I have given different arrival times. Can you practice this and get me the average waiting time and turnaround time of all the processes? I am here only sitting next to you guys. Try. You should try it by yourself. Then only you can get certain practice. If you don't practice, you may solve the question but not quickly. That will give added advantage to other opponents or other aspirants who will be able to solve the questions quickly. If you are able to solve a question but in 5-6 minutes, which is known type of question, then Other fellas are able to solve such kind of questions in 2 to 3 minutes. So they are getting 2 minutes, 3 minute extra for such kind of a question. And if that happens for 10 questions, then they will be having 30-minute extra over you. Okay. At time 0, we have only one process arrived P1, which arrives first, arrived already, it will run for 6 time unit. When P1 was running till 6 time unit, till then, before that, P2 arrived at 1, P3 arrived at 2, P4 arrived at 3, P5 arrived at 4, and these all already arrived and sitting and waiting. Now, which process will run next as per the arrival time? This is gone. Among remaining processes, which one will run next? As per the minimum arrival time, P2 will run next. P2 will run next for 2 time unit till 6 plus 2, 8. Then next arrival time 2, P3 will run next for 1 time unit till 9. Then P4 will run next plus 4, 13. At the end, P5 will run next plus 3 till 16. This is how you are going to solve this particular. Understood? Now, completion time, turnaround time, waiting time. From the Gantt chart only, we will fill up first completion time. Completion time of P1 is 6, P2 8, P3 9, P4 13, P5 16. Then turnaround time, completion time minus arrival time, 6, 8 minus 1, 9 minus 2, 13 minus 3, 16 minus 4. Waiting time, turnaround time minus burst time, 0, 5, 6, 6, and 9. Somebody has posted an answer. Let's see if average turnaround time matching with that answer or not. 10 plus 12, 22 plus 14, 36 plus 6, 42 divided by 5, which is 8.4. And average waiting time is equal to 26 by 5, which is 5.2. Check it out. Okay, now some small things I'll have to tell you. First thing, when you are executing these 5 processes, how many times context switch occurs? Context switch means one process stops running, other process starts running. This P1 stopped, P2 runs, one context switch. P2 to P3, 2. P3 to P4, 3. Then 4. Total 4 number of context switch are here. So if somebody is asking number of context switch, then answer is 1, 2, 3, and 4. 4 context switch are there. Another thing is total how much time processes are running. P1 runs for 6 time unit, P2 runs for 2, P3 runs for 1, P4 runs for 4, and P5 runs for 3. Total 6 plus 4, 10, 13, 14, 15, 16. Total 16 time duration CPU is used. Look at this. From here to here, total 16 time duration CPU is used. So you can have another checking over here that summation of burst time will be here. In general case, another case also I'll explain. Look at here. Look at here. 28 plus 4 plus 4. 28 plus 8, 36. 36 summation is here. This is another check. Sometimes what happens in these summations, students may make a mistake. You can cross check that do we have this as summation of all the burst times or not. If CPU is used all the time, this summation of burst time will be equal to here. But there is another issue. Another issue is what? When there is no any process to run, then CPU will be free for some time. And when in between, in the middle or somewhere, if CPU is free for some time, then that particular time is called as CPU idle time. And that particular time can occur in such kind of a question. Look at this. What happens? The Gantt chart starts from 0, but at time 0, there is no any process arrived. Look at this. This process is arriving at 1, 4, 6, 8 and 7. There is no process at all at 0. If there is no any process, then what you will execute? CPU? Nothing. CPU will be sitting idle, not doing anything. So in that case, for one duration of time, CPU will be idle. Idle means will not do anything. For one duration, why? Just because at one time unit, P5 arrives, then CPU can get that process P5 and run it. So when P5 runs, for how much time it will run? Till 2. Plus 2, 1, 2, 1 plus 2, 3. Till 3 time duration, 3 time P5 is running, yes, but after completion of P5, again the issue is no any other process arrived. This is arriving at 4, this at 6, this at 8, this at 7. Process P4 did not even arrive till 3. So P4 is arriving at what? 4. 3 to 4, CPU will be again idle. Then at 4, P4 runs for one time unit till 5. Now at 5, there is no any process again. To 5 to 6, again CPU will be idle. And then next at 6, P3 arrives. 3 time duration. 9. Then next till 9, these two arrived, yes. So you can run them as per their arrival. First P1 arrives plus 4 and then P2 arrives plus 2, 15. Now look at this. Between 0 to 15, time duration total 15. Among that time duration 1, 2, 3, total 3 duration time, the CPU was idle, was not executing any process. Look at this. 4 plus 2, 6 plus 4, 10 plus 2, 12. CPU usage time is 12, but 3 time we have for idle period. 12 plus 3 is 15. Here we have 15. The rest of the things are same. Arrival time, completion time. Completion time from here I'll take. Completion time of P1 is 13, P2 15, P3 9, P4 5 and P5 is 3. Same completion time, whatever you have is the same. Then based on that turnaround time, waiting time, same to same you can calculate. Additional thing was when CPU is free, there is no any process executing. This will be total free time plus summation of burst time, 12 plus 3, 15. In such kind of a question, when CPU remains idle for certain duration of time, we have some aptitude question. Percentage of time CPU idle. Total 0 to 15, we have 15 unit of time. But in those 15 unit of time, how much time CPU is idle? Free. So I will write percentage of time CPU remains idle. Free out of 15 into 100%, which is 20%. Similarly, percentage of time CPU used. boss, 12 unit time CPU used among total 15, 100%, 4 by 5, which is 80%. These 2 points are clear to you guys? These are clear to you guys? Check it out. Okay, further, if this is clear, then in FCFS there is a problem of convoy effect. And what is that? If a big process which takes a lot of time in CPU is scheduled first, then that process only will keep running. If that process is only running, other processes will have to wait. Let's say user is running one process, that process is running. Now user has given another process to run, but that process is not running. User will have to wait. That process will run once the big process completes. So user will feel, when I have submitted my next process, then too it has taken a lot of time to respond, the computer system. Why? Reason is why we know that, but user is not actually feeling good about it. User is feeling like my system is very slow yaar. I have initiated a process, but that process response was very slow. Nothing was executing, nothing was coming out. That is convoy effect. One big process delays the execution of other processes and makes the system slow. So convoy effect is, if a big process is scheduled first, then the then this process delays execution of other processes and makes system slow. That is called as convoy effect, and this convoy effect only occurs in FCFS. FCFS, the only algorithm, suffers from this convoy effect. Okay, to solve the convoy effect, what we will try to do? We will try to schedule a smaller process first so that it can completely execute quickly in lesser time, and then other processes can also run and give the response to user that, okay, when it is running, I can see my process is running earlier. Quickly it is running. Further, so next particular algorithm is SJF based on that solution. But before that, let's analyze FCFS. FCFS is very easy to implement. Use a queue data structure and we are done. As in the sequence processes are arriving, we keep adding them in a queue data structure and remove a process from queue data structure and execute. Simple. No starvation. What is the starvation? I'll explain you it in the SJF. But here in FCFS, starvation is not there. There is no any complex logic to implement. Preemption option is not there. That is the disadvantage. If a process is running in CPU, process cannot be forcefully preempted. And next, convoy effect makes the system slow, which I just explained you guys just now. Further, SJF. This is the solution of convoy effect which is happening in the FCFS. Yeah, okay. Look at this. shortest job first, scheduling criteria. In shortest job first, the scheduling criteria is the burst time. The process which is having smallest burst time should be scheduled first. So previously in FCFS, smallest arrival time we were checking out. Here I'll have to check the burst time. So what I'll put up the formula or the scheduling criteria is smallest burst time process first. But you tell me, can you schedule a process at 10:30 p.m. for running in CPU which is going to arrive or which will arrive in future at 11? Can you schedule a process at 10:30 only, that 10:30 at 10:30 this process P1 will go for execution, but the process has not yet arrived. Process will arrive at 11, but we are scheduling the process to run now at 10:30 itself. Can you do that? Can you do that? Can you schedule a process even though process has not yet arrived? क्या आप कोई प्रोसेस को तब शेड्यूल कर सकते हो जब वो अराइव ही नहीं हुई है? पॉसिबल? ऑफ कोर्स नॉट. सो SJF process execution algorithm will be working on only those processes which have arrived already. So you need to check what all processes arrived. Among them, which process next I'll have to run. You don't check all the processes just because among all the processes, there can be some processes which are smaller in burst time but not yet arrived. If process has not yet arrived, how can you schedule it first? Right? So remember that. So smallest burst time process first, but among the processes which have already arrived. Okay? And if two processes are having equal burst time, then tiebreaker is FCFS, which means first you need to check their arrival times. Whichever process is having smaller arrival time, scheduled first. But if processes are having equal arrival time also, then go for process ID. So burst time, if equal, then arrival time, that also equal, then process ID. Don't directly jump for the arrival time. Don't directly jump for the IDs. First check the arrival time, okay? FCFS arrival time first. Type of algorithm, again this is non-preemptive algorithm. You cannot preempt a process after scheduling. Let's solve the same question which we have solved for the FCFS. Now look at this. Three processes are there, P1, P2, P3. My Gantt chart starts at 0. At time 0, what all processes have arrived? I'll have to check what all processes have arrived. At time 0, all three have arrived. If all three have arrived, then among these three, as per my scheduling criteria, shortest job first, which one is having minimum burst time? 28, 4, 4, 4, 4 are minimum. So two processes I am getting, P2 and P3, both are having minimum burst time. Now among these minimum burst times, which one should be scheduled first? If there is a tie, then I'll check the arrival time. Arrival time, which one is having smaller? Both are equal. Tie here also, then I'll check the process ID. Process ID, smaller process ID, P2 should be scheduled first till 4. Now, P2 completed? Yes. Remaining two processes, P1 and P3. Which one is having smallest job first, shortest job first? Smallest job, P3. P3 will be scheduled next till 8. At last, P1 is remaining. That P1 will run 8 plus 28, 36. Now, completion time. Look at this. Sequence is changed. P1 completes at 36. P2 completes at 4. P3 completes at 8. Please be aware the sequence of the process execution may change as per the algorithm. So please fill these entries carefully from the Gantt chart. Turnaround time, completion time minus arrival time. Waiting time, turnaround time minus burst time. 36 minus 28, 4 minus 4, 8 minus 4. Look at this. Average turnaround time is what? 48 divided by 3. 16. And average waiting time is what? 12 divided by 3 is 4. Oh my god. Same question when we have solved. Processes were having on an average 20 unit waiting time per process. But same process scenario when we were solving using SJF, then average waiting for each and every process is just 4. Drastically reduced, yes. Why? Just because we have solved or we have scheduled that process first, which is the smaller one. So remaining all processes will not have to wait for longer to run. This is SJF. Let's try this question. Will you try it first? I'll give you 2 minutes to solve this question and then I will explain. Try it. You guys try it. Remember that here the processes are not arriving together. So you need to schedule that process first which has arrived. Don't schedule the process which will arrive in future. Remember that. You can't schedule future processes. I am sure you guys are trying. I can also solve along with you guys. At time 0, we will have to check what all processes have arrived already. Just because I told you guys 3-4 times, you can schedule that process only first which has arrived. At time 0, there is only one process P1 arrived. All other processes will arrive in future. You cannot schedule future processes. You need to schedule the current process. So whichever arrived among them, only single process available. I don't have any choice. I'll have to schedule this P1 process first. P1 process till 5 time unit. After that what? Till 5 time unit, these processes have arrived. When all these processes have arrived, which is the smallest process? Now I have choice of 4 processes. Among these 4 processes, P2, P3, P4, P5, which is the smallest one I can select? Smallest one is this P5. P5 will run for 1 time unit till 6. Next, till 6, this also arrived. Okay, so I have now again 4 processes, 1, 2, 3 and 4. These 4 processes, smallest I will select with burst time 2 P4. Till 8 it will run. Then next, smallest process is this P2 plus 3 till 11. Then P3 plus 4, 15. Then P6, 21. Let's cross check it. Total 10, 15 plus 5, 20. Oh, 15 plus 5, 20 it is. Not 6, 20. Cross checked. There was a mistake. I have made plus 6, but it is plus 5 only. Done. Simple. Remaining things you guys can fill up, can come up with average waiting time and turnaround time, how it will come. As many as questions you will practice, you will become quick in understanding how to solve a specific type of questions. And if you become quick, it will be a great advantage in GATE examination. Why? Just because if you can solve known type of question, which method is known to you, the questions are known to you. If similar kind of questions which we have solved already in practice PYQ classroom somewhere, if you can solve such questions in GATE exam quickly, then you can spend extra time for new type of question which are new, you haven't seen, you will have to try exactly how to solve them. And if you get more time on that, you may have, or of course you will certainly have, probability higher that you can get them corrected and you can increase your score. This is how toppers are making get better score in examination. The advantage of SJF is among all the non-preemptive algorithms. SJF is also non-preemptive algorithm. So among all the non-preemptive algorithm, SJF provides you minimum average waiting time. So all the non-preemptive algorithm you apply on a given scenario of process, among them SJF will always provide you minimum average waiting time and minimum average turnaround time. Minimum average waiting time and average turnaround time among all the non-preemptive scheduling algorithms. Better throughput in continuous execution. If processes are keep coming, then it can run more number of processes per unit of time, per second or per minute. Just because of smaller processes we are executing first, so more number of processes we can execute in 1 second. Disadvantages are more. First disadvantage is this is not practically possible. Why? Just because how operating system will understand that which process will run for how much time in the CPU actually. How operating system will understand if a process arrives, it will take how much time exactly to run on CPU. A process can run for any unit of time. So burst time is not known in advance. Hence practically this algorithm is impossible. Second thing is preemption not possible. Once a process scheduled, it will run completely. And third problem is starvation. What is starvation? Long waiting for some processes and indefinite waiting. Indefinite. It is not definite. It is not fixed. I'll tell you. Let's say there are 3 processes, P1, P2, P3, arriving at time 0. P1 is having burst time 15, 3 and 2. Such kind of burst times are coming. Smallest process P3 will run, then P2 will run. When P2 and P3 were running, P1 was waiting, but during execution of P2 and P3, 2 more processes are coming, P4, P5, and their burst time is smaller than this. So if burst time is smaller, then P1 will have to wait. Let's say P4, P5 executing, P1 is waiting, and during P4, P5 execution, 3 more processes are arriving, which are having smaller burst time. This process will not get CPU. Processes are keep coming and they are keep getting the CPU, and this process is just waiting till what time? When processes will stop coming, then only this process will get the CPU. Or if coming processes are bigger, then only this particular process will get the CPU. But it is not definite. It is not fixed that when P1 will get the CPU. So it may possible that larger processes may have to wait for indefinite time. A larger process or longer process may suffer from starvation, indefinite waiting. But this indefinite waiting does not work in FCFS. Why? Just because in whichever order processes are coming, they will get the CPU eventually. So a process already arrived and waiting for long, later arriving processes are executing before that doesn't happen. Here later arriving process also may run before this process just because the criteria. And that's why FCFS no starvation, here we have starvation. I hope you guys got that point. In FCFS, no starvation, just because in whichever order processes are coming, they will execute eventually. If P3 arrives after P1 and P2, then P3 will run after P1 and P2. P4 will not run before P3. P5, P6, P7, P8, so many processes arrived after P3. Still, P3 will run first, then later on all these processes. But in the case of starvation in SJF, it may possible that P3 is a very large process and it will wait. P4, P5, P6, P7, 8, 9, 10, 11, 12, those are coming and executing just because those are smaller processes. My scheduler chooses smaller processes. P3 is waiting and waiting. Till when? Nobody knows. Just because smaller processes are keep arriving, big process keep waiting. Starvation, indefinite waiting. Okay, this is it for today. Tomorrow we are going to discuss SRTF algorithm, and along with that we are going to discuss the other examples like LJF and other examples. Sure. So I hope you guys are clear for today's lecture. Please go through today's lecture once again before you come for tomorrow. You will be having better learning. Okay, thank you so much. Have a great day.